Hello guys, welcome on Tesla Adventures. In this video today we are going to discuss the Maxwell's law of distribution of velocity. Now we already know that this in KTG kinetic theory of gases we discussed that each molecule of an ideal gas moves with a different velocity, and therefore there was a scientist called Maxwell who plotted the variation of Fv with the speed of the molecules, different speeds of the molecule practically. So this is a practical graph, and this Fv is called as probability density function, and it is actually dn by n upon dv. Now it is dn by n is the fraction of molecules which are moving within the speed range of v to v plus dv. So if these are the number of molecules, dn are the number of molecules and n is the total molecules, then dn by n is the fraction of molecules which are moving within this speed range v to dv. So this is the probability density function, which is dn by n by dv. So he plotted this curve between probability density function and the speed of the gas molecule, and he derived this conclusion, a mathematical conclusion, that Fv is equal to 4 by root pi into m upon 2 kt. There m is the mass of one molecule of the gas, k is the Boltzmann constant, and T is the temperature. To the power 3 by 2, V is the variable speed of the molecule, and this is m v square by 2 kt with a negative sign, e to the power. So this was the conclusion of the Maxwell's graph, and this, if we talk about a single graph at a single temperature, so this was the graph you can see. Now you can also see that the peak of the graph will represent the highest fraction of molecules which are moving with this speed. So this peak of the graph is also called as, the speed at this peak is also called as the most probable speed, because as the name suggests that it is the most probable speed by which the most number of the molecules are found to be moving. Then this is the average speed, this one is the average speed, and this is the RMS speed. Now we already know that these three velocities, we have already studied their formula, so let us discuss their formulas. And you can see that these three graphs are different three graphs, and you can see that the temperature of this graph is least. Then if this is the temperature T1, this is the temperature T2, and this is the temperature T3, then we can surely say that T3 will be greater than T2 will be greater than T1, due to the fact that on increasing the temperature, this peak of the graph is shifting in the forward direction, and we know that all of these velocities depends on under root of temperature. So if we increase the temperature, then these velocities will decrease. So this is the Maxwell's distribution. Now let us talk about the most probable speed, VMP. We know, we already have studied the formula of most probable speed, and you can see that most probable speed is the least speed which by which the molecules can move. So this is among these three speeds. So VMP, we have studied that V most probable is equal to under root of 2 kt by m, or we can also write it down as under root of 2 RT by capital N. The difference in these two formulas are the fact that R is the gas constant, K is the Boltzmann constant, and this m is the mass of the molecule, and this m is the molar mass of the gas. Now let us try to derive this formula of most probable speed. We know that F as a function of v, which is the probability density function, is this one, 4 by root pi. Let us write it down on the next page. So yeah, 1 second. So this is the probability density function. You can see that. Now we know, let us assume that this is let us write it down here. Okay, so let us assume that this complete is A and this is except B, V square, this is B. So let us write it down, Fv as A V square into e to the power minus B V square. This is the probability density function. And now we know that to find out the most probable speed, obviously most probable speed is the speed with which most number of molecules are moving. So we know that for most probable speed, this function Fv would be maximum, and therefore we differentiate this function and we use the maxima minima technique. So differentiation would be done by the u into v method. So this is v square multiply by differentiation of this term, and differentiation of this term would be minus b into 2v e to the power minus b v square plus, now we will differentiate v square and we will take this common, minus bv square into 2v, and we will equate this to 0. So we can say that you will see that this 2v and 2v will be cancelled out, this e to the power minus bv square and e to the power minus bv square will be cancelled out. So finally there would be v square into b will be equal to 1. So v square into b will be equal to 1 and v square will be equal to 1 by b. So v will be equal to 1 by root b. Now b was m by 2 kt. You can see that this is b. So 1 upon root b will be under root 2 kt by m. So this is the most probable speed, which is under root 2 kt by m, and we can also write it down as under root 2 rt by capital M. Okay, so this was the most probable speed. Now if we move further on the average speed, so V average, we already know that V average is under root 8 rt by pi m, and this is capital M. So if we wish to find out this average speed, we have already written the formula Fv as AV square e to the power minus BV square. So Fv is AV square e to the power minus BV square. This is probability density function, and we know that to find out the average speed, the formula of average speed should be integration of v into dn 0 to infinity upon integration of dn. Now 0 to infinity. Now you can see that you can imagine that how I have created this formula. You can see that VDN, if let us suppose that there are 5 molecules which are moving with the different speeds, then we would find out their average by V1 plus V2 plus V3 plus V4 plus V5 upon 5. So this is a continuous function, so we cannot use summation. So we are using integration, and therefore the term would be VDN, integration from 0 to infinity. Now this VDN is actually the addition of V for the number of times that how many molecules are existing. So this is integration v dn, and the limit of this graph would be 0 to infinity. I'll tell you why. Because if you see that fv is dn by n by dv, so fv will be av square e to the power minus bv square. So dn will be equal to a into n into v square into e to the power minus bv square into dv. So ultimately this v average would become integration 0 to infinity. This is a n v cube, in fact yes, v cube, e to the power minus bv square dv, divided by integration 0 to infinity integration of dn. So this is a n v square e to the power minus bv square dv. So you can cancel out the constant terms and you can integrate on both sides with respect to dv, and you can put the limit 0 to infinity. See, this integration would be a difficult one. In fact, it would be done by the integration by parts Eilate method, and this Eilate method could be applied on this integration, and it might be possible that you might face a situation where you have to substitute the values of v square also in terms of some other variable. So it is a lengthier process, so I am not doing that and I am skipping that. So v average, directly I can write it down, will be under root 8 kt by pi m. And this case, again the Boltzmann constant and m is the mass of one molecule. So if we multiply with the Avogadro number on the numerator and denominator, then v average can be written as under root 8 rt by pi capital M. So this is the average velocity, in fact average speed of the gas molecules. And it is very important to note that in many exams I've seen that there is a simple bluffing question which is given to check the awareness of the student, that the average velocity of the gas molecules in the gas is 0, obviously, because they are moving randomly and their net average velocity is 0. Because if you say that the net average velocity of a gas molecules is not 0, then you are saying that the complete gas is moving in some specific direction, which is not the case. You could not see any vessel containing a gas and it is moving on its own. So this is not the case. So average velocity is 0, and what we have derived is the average speed of the gas molecules, which is under root 8 rt by pi m. So you should always be aware about the fact that what is being asked in the question. Now let us discuss the root mean square velocity. So this is root mean square velocity. We all know that root mean square velocity is under root 3 rt by m, and we have already derived this root mean square velocity 2 times before in the previous videos. So this root mean square velocity is actually the square of velocities, then their mean, v1 square plus v2 square up to vn square by n, and integration from, in fact this is mean and root. So this is root mean square. What we have done, we have squared the velocities and then we have calculated the mean of their squares, and then we have applied a root over them. So this is root mean square velocity. So to find out this velocity, what we have to do is the fact that Vrms will be equal to v square into dn integration divided by integration of dn. This is the square and mean, and then we have to put a root on it. So V average, by using that function you can find out the V average. In fact, this RMS. So V RMS would be under root 3 kT by m. This small m is again the mass of molecule, K is Boltzmann constant. So again, if we multiply denominator and numerator by Avogadro number, we can write it down as 3 RT by capital M, where m is the molecular mass. So you can see that the highest velocity is Vrms, and then it is V average, and the lowest velocity is V most probable. So we can say that the least number of molecules among these three velocities are moving with the highest velocity Vrms, and the most number of molecules are moving with the least velocity Vmp. Now let us take an example of that Maxwell distribution, and this question was asked in JEE. So in this question there is a graph given between Fv and V, where V is the speed of the molecules, and this is an imaginary Maxwell distribution graph, and Fv is dn by dv. It is not dn by n dv, in fact it is dn by dv in this question. So we have to find out the average speed and the root mean square speed of the gas molecules. So you can see that first of all we have to find out the total number of molecules present in this gas. So you can see that if we find out this small area, then this would be dv and this would be dn by dv. So if we find out the small area dA, then it would be dn by dv into dv. So it would be dn. So area of this graph is representing the number of molecules, and if we integrate then we can find out the total number of molecules, which would be integration of dn. So the total number of molecules will be the area of this graph, and area will be half A into V. This is the total number of molecules, and A into V is equal to twice of NT. NT is the total number of molecules. Now we have to find out the average speed and the root mean square velocity speed. So let us use a page. So we know that in this graph, if we write the equation of the graph, then that equation, this is V0 and this is A. So slope would be tan theta and it would be A by V0, and the equation will be y is equal to mx. So y is dn by dv and m is the slope, which is A by V0 and into V. So this is the equation of this graph, and dn is A by V0 into V dv. So we know that V average will be integration of V dn upon the nt, total number of molecules, and limit we would use in the later part. So V dn integration would be A V square by V0 into dv, and limit would be 0 to V0, because here the maximum possible speed is V0. So this is, and this is n total. So you can see that this would be A by V0 is common, this is n total, and the integration of that would be V cube by 3, and if we apply the limits then it would be V0 cube. So this is A by 3 nt into V0 square, and you can see that A V0, this is A V0 is 2 nt. So this is 2 nt into V0 by 3 nt. So V average in this case will be 2 V0 by 3. So this is the average velocity of the gas molecules in this imaginary gas. Now let us find out the value of RMS velocity. So we already know that dn is equal to A by V0 into V dv. dN is equal to A by V naught into V dV, and V RMS will be the integration of V square dN upon N total, and again V RMS can be written as integration of V square into dN is A by V naught into V dV divided by N total. The limit would be from 0 to, in fact, V naught, and the common term would be A by V naught N total, and integration would be V naught to the power 4 by 4. Okay, so now what we have to do, we know that A V naught is 2nt, so we would write down it as 2nt. So this is, we have to apply a root also over it to find out RMS. So A V naught is 2nt, so this is under root of 2nt upon 4nt into V naught square. So you can see that it is V naught by root 2. So V RMS in this case will be V naught by root 2. So this is the complete analysis of Maxwell distribution of velocity, and I have also discussed this concept illustration problem which was previously asked in JEE. So I thought that it would give you a better understanding of Maxwell distribution and the type of questions which are being asked in this topic. So in the next video we'll be bringing some more concepts of thermodynamics. Thank you.